Yeah. So I was muted until then. I'm covering the R help session. And like I said, the three main topics covered since the last exam were model building, transformations, and logistic regression. And that's I think, increasing importance. I think the main differentiator between the good grades and the bad grades on the midterm are going to be who can do the math for logistic regression. Not saying to do it real hardcore, but just so you can get probabilities from log odds, you understand the concept of log odds, and kind of how you can work with it. Okay, so there was the practice exam, which I hope most of you all have gone over, and yes, there were some issues with the practice exam. I think some of them were fixed in the last day, but you probably didn't even notice it if you did a few days ago. And so I was thinking that I could cover any first questions with that, and then I can kind of go over emphasize what I think is most important, probably what's missing most from your knowledge before the midterm, if that works for you guys. Again, this is pretty open-ended. There's no real formal script I'm following. I put kind of an outline of stuff to cover if no one's speaking. Else, I'd prefer if I just was more of a conversational thing.
So were some of the answers to the practice exam wrong?
Yeah. Yeah.
Can you explain number 3 on the practice exam?
Yeah, sure. I'd be happy to work like that. Okay. Number 3. So when I look at this graph, what's the first thing you see right away? I mean, what does it scream? You see what they're trying to demonstrate, right? What? I'm sorry? Yeah, the equal variance of heteroscedasticity. Hopefully at this point you just see a cone shape and you immediately think something's bad, because cones aren't linear regression. So we can see that the volatility of this is increasing this way. And so this is a good cover of kind of what we're doing with transformations. So first off, why do we do transformations?
To make them all fit.
To make them all fit. In what specific ways? Like where would we be doing that? Yeah.
To like fit certain like linearity assumptions.
Yeah. So we have a linearity assumption that's not being sufficient. That would be a good example of when we would do it. When's another example? So how about this one right here? So I mean, heteroscedasticity, if that's an issue, and then linearity kind of ties with that non-normality. So basically, we're fixing some of the assumptions because I think that a linear regression might not be appropriate here. We'd rather see like an exponential. So whenever you're doing these transformations, you first try and think to yourself, what am I trying to do? And I always imagine myself kind of squishing or expanding out what's going on here. So what direction do we need to go here? What's the problem first off? Do I need to squish something, or which direction's bad? Up and down or left and right? Yeah, up and down, right? Like everything's really kind of fine left and right. I really can't do anything. It's hard to do it without so on the board. But if I expand it out like this, is that going to help anything? And if I like constrict it like this, if I bring it in, that's just going to make it worse, in fact, right? Because then it's going to be more cone. So I have to go up and down, right? That's the first thing I'm saying. So which parameter am I transforming? If I'm trying. Exactly. Yeah, the y variable. So I don't know which one that is. So here, yeah, size. That's the y variable. And all right. So options of exponential and log. Which one does what?
Exponential makes it wider, right?
Yeah. So exponential is going to stretch it out, and log is going to do the opposite. It's going to constrict it, squish it. That's just a fancy word for it. So it's going to squish it. And the reason why, if you think about how a log works, exponential, something that's big, exponentiate it, it's going to get way bigger. And the small ones aren't going to get nearly as big. The rich get richer, the poor get poorer. And with log, it's the opposite way. Like the big numbers get brought in more than the small numbers. So that's why we use log a lot. All right, and so what's going to be inaccurate here? Why do we want to fix this.
So your predictions will be good.
All right, so is it going to change where the line is if I do this? Yeah.
If you did do the log transformation, would the values on the far right side be the ones that were changing, and the ones on the left would technically still be accurate, so to speak, or the variances would?
Yeah, so we don't actually know that because we're not constricting or expanding the x variables. So if it was actually like a flat line, let's say the regression is actually that 0, it's like a flat line, it wouldn't be doing anything, right? So yeah, we can't really tell that. Whenever you're doing these transformations, you're not trying to change what the overall like prediction is. You're trying to fix the heteroscedasticity. What's the problem with heteroscedasticity here?
It's like it funnels out to the right, like the variances get really big as your values.
Right. So if it's fanning out, does the middle of the fan change if we bring in the fanness or fanness? No, the middle is going to be the same place. We're just constricting it. So like our prediction's actually right. I mean, the average for these values is somewhere, I would say, around here, right? And then the average for these values is here. So our overall prediction's right. Like we're giving probably the best estimate with this regression. The problem is that our errors are going to be different at different places. So like we're going to get the same error band here as we are over here, even though when we look at the graph, we can tell that we're going to be way more accurate here on the left. Okay. Does that make sense? I'll repeat that. So you have the same estimate here. We're not changing our estimate. Like the average of these values is probably somewhere around here, right? And the average of these values would be over here. So we're not fixing that with this transformation. What we're fixing is the fact that we're actually way more accurate over here than we are over here. Yeah.
So if those points were just say like scattered at random points above and below that middle line, then you could say all predictions would be inaccurate, right?
Yeah, if I never hit the middle line, you know that you're not accurate, and that'd be a violation of non-normality actually. So when you're looking at the residuals, it would be like bimodal. Or, yeah, we're not covering that one, but that's right. Yeah. Okay.
Why don't you use like an exponential transformation?
So if we did an exponential transformation, what would be going on is like, what's the exponential of 200?
Oh no, I mean when would you use it?
When would we? Yeah, this is why I like the whiteboard for this. So my way of always thinking of the transformations is this. What's the problem here? It's non-normal, right? I mean, it's not linear. You can't really draw a linear line here. But these values here, right? They're I kind of need to put these out, you can see, to make it more linear, right? So if I did an exponential transformation, it would actually turn more into this.
If you did exponentials.
Yeah, exponential on the x's. Because these values would get stretched out a lot more than these values, right? And you know what's the cheap way of figuring it out? Doesn't this look like how an exponential curve looks like? I mean, that's actually what you're doing. Does it look like how an exponential curve, you know how an exponential curve like shoots up like that? If the data looks like an exponential curve, an exponential transformation is good.
Are you in the transformation on the x variable?
It's on the x.
Yeah.
If you did it on the y, you can just invert it though. That'd be a good one for exponential on the y. That'd be log. Yeah. I mean, the main way you do is you test it out, but exponential is a lot rarer than log. Log is kind of like the go-to one for most people.
So do you just draw like graphs of when you might use the other functions?
Yeah, there's a lot of those. I could be here all day if I did that. I would say that just be sure that you know. See, the way I do it is I actually imagine in my head what the transformation would do. I mean, that's really the best way to do it. Because in real life, you just try them out. That's what you do. Think about what you're trying to fix, because
So
the
inverse
questions are
might be
really
a log.
going after, like, what are you trying to fix here?
The inverse might be a log.
Inverse?
So if you had the inverse of that, if it was like curved, but kind of like towards the flat.
Yeah. One way of looking at that is if I exponentiate the y. That's the same thing as doing the log of beta x plus epsilon, right? That's why they both kind of work.
Oh, so exponentiating y is the same as log x?
It's not. I don't want to get too much into it, but it's kind of like that, yeah. Yeah. All right. I think that the transformations are a lot less big in the logistics. I don't want to spend too much time, but I would say for looking at, like, the question where it's looking at the graphs here, I mean, really just know what you're trying to go after. I mean, so why is this one not great? Yeah, it fans out. I mean, is this one very good? No, it curves. And then, like, when I look at this one, for example, like, what kind of transformations are you imagining? Exponential? Exponential on what variable? On x. So we want to put these ones further out and put these ones. So you want to expand it out this way? No, that doesn't look right to me either. How do we transform this one?
Try logs.
Square root.
Yeah, logs are a good one. Logs pretty much fits most of these, because that would bring these big ones in, right? Log of y. That's how I like the way that one works. Personally, I think 1 over x would be pretty good, but apparently that causes some pretty bad problems with heteroscedasticity. And the reason why I say 1 over x, because to me this looks very asymptotic, you know? It's kind of like what does this look like from when you're looking at graphs and when you're first learning kind of functions. Okay? So thinking like that, I think that's the main way to do well in this. Yeah. Sorry, is this helping? Yeah.
For the logarithmic transformation,
Uh-huh.
on the left side of the graph, wouldn't it make the graph too small instead of wider? On the left side, on the graph top left.
Top left? Yeah, this is the unchanged graph. And so it actually has the log of the y. And you can see that these tall values here, they're brought in. So apparently like the log of 80 is something like 4.5. And these aren't moved as much, so they're left over here. Yeah. And you see square root is kind of similar to log, but doesn't do quite as well. So it kind of straightens it out too, but not as well as log. And then, yeah. Okay. So actually, you can kind of think, how would I transform this one again to try and make it better? I wouldn't go this far, but what could I do to fix that heteroscedasticity? You take the log of that, right? Yeah, that might help.
Of the y or the x?
Of the y again. Yeah, so doing any transforms on the x doesn't really change the heteroscedasticity, because your heteroscedasticity is like a problem of each x value. That makes sense.
Yeah.
Yeah. Yeah. Unfortunately, I don't think there's there's like one trick to doing all these, kind of just being able to speak it.
On number 15,
Uh-huh.
was that one of the questions that was wrong?
I think it is. Let me look at it again. Yeah, I think this was. I forgot if I missed this one or not. But if you're doing the predict function, that should do you. We can
Can we run
do it
through
together.
these
You want to run
models?
through it? Yeah. So I think I have.
So,
Yep.
on 14s, why did we only use two predictors to model when they gave us like four?
I mean, you can use as many predictors as you want. I mean, it was asking specifically for those two predictors. I mean, in real life, you're not using every predictor that you're given because, I might be making a model for this, but I want to figure out certain things. You only want control for things when you mean to, Does that make sense? Yeah.
I was just confused though, like just to extend on that, because they gave us SAT, high school GPA, and extracurriculars, but they only included SAT and high school GPA, without even telling us that extracurriculars shouldn't even be there. Should we have studied it first and been like, oh, extracurriculars is easy?
Well, they don't tell you what the extracurriculars are. You need to you can't just assume extracurricular. And it's ideal there not to assume a value because, you don't know about what the correlation is for extracurriculars with GPA. So it's better to just not control for it if you don't want to include it in your model.
So can we have it in our model when we build it and then just give this 0 when we do the predict?
No, that would be incorrect because then you would be saying specifically for someone with 0 extracurriculars and that GPA. If you don't know their GPA, if you don't know their extracurriculars, you just don't control for it. You have to exclude it from the model. It'll be a different model.
I guess my question would be then, how are we supposed to know to leave extracurriculars out of the model?
Yeah, I guess it wasn't extremely clear on that, but if it's asking a question where you only have information about the SAT and the GPA, you should only control for that. Don't assume things where you don't have information, unless it's stated. All right, so I'm just load up the data. It's called dat, I think. I don't know why my R is acting weird. Here we go. Yeah, so I've got this, and I'm making a prediction, and I use GLM of if I'm admitted or not as a function of high school GPA and SAT scores. That equals that, and this is going to be a binomial regression. Okay. And then when I look at summary of M1, you can see as you predict, the higher GPA is, the more likely you are to be admitted, and the higher your SAT scores, the more likely to be admitted. Okay. And so the question asked is 15. Predict Chelsea's probability of admission. She got a 1200 on the SAT and has a GPA of 3.0. So I'm just going to do it in the pure technology version first. So we're going to do predict.glm. Or you can just do predict. It'll figure out that it's a GLM on its own. And a reminder of how predict GLM works. Use the question mark. So I'm going to put in an object. That would be our model. And my new data is equal to a list where high school GPA is equal to what? 3. And SAT is equal what? 1200. All right, and then the type, this is kind of tricky. We're actually looking for something called a response. I'm not going to go too much into it because it's a feature of using a general linear model. That gives us our prediction, which ends up being 0.806299.
Can you just go really quickly how to do a range? How to do an interval?
Okay, so yeah, the question I think asked, is that on the homework? Was it that it asked for like a prediction interval? And you don't really do that with logistic regressions. That was a typo. You're really asking for the confidence interval. Okay. And then the confidence interval, Ryan did a really good job of explaining it on the announcements. I think that's probably the best one. But essentially, we're building a confidence interval like we did in Stats 309, or I think we covered it slightly in the beginning of the class, where we have the middle, which is our main prediction, our fit, and then we add and subtract the basically the range of the confidence interval, which is the z value, so how much confidence we want times the standard error. Okay, is that familiar? I do some puzzled faces and some not.
So we're gonna have to do that. We're gonna have to do it, right?
Yeah, basically by hand.
How do we know what the z score is gonna be?
So whenever you get the confidence interval, that's how you figure out the z scores. So the way you do the way the confidence interval works is that we have some middle value, right? So this would be the main prediction. We'll call it beta, or prediction hat, right? Right, that's our best estimate. That's the fit, and then it goes left and right based on. We assume it's like a normal distribution here, and we're saying with a 95% confidence interval, basically that there's 95% of the probabilities contained in this range, and it's symmetrical. Okay? So with 95% included in that range, how much is over here if these are symmetrical?
2.5%.
Yeah, 2.5, 2.5. So it's really easy. All I'm doing is I'm figuring out a normal, Q norm. You look here is Q norm, which means that I'm getting a normal distribution. I'm trying to figure out where it is that 2.5% of the data is contained on the left. Okay, so I want 0.025, and I'll just assume a mean and standard deviation of normal. So that's the negative version of it, and so you can just use the positive version. If I wanted the positive version, I would just put in, it's the same thing, 97.5. I'll give you the same value, positive. So that's basically, I want 2.5 to the left, or I can figure out where 97.5 is to the left.
And that gives you the z-score for the 95% confidence interval.
That's for 95%, yes.
Okay. So you just multiply that by the standard error and then add that on to the mean and subtract it from the mean, and that's your range.
Yep.
Do you mind sharing the screen with this site?
I try to figure out how to do that. If anyone knows how to, I've been told you can do it, but I've never been able to do it even. Does anyone know how to do it? I would be happy to. There's some more seats. There's a seat over there and there if that helps. Sorry.
Oh, I'm sorry, I don't know how to do that. So to quickly go back to that predict function that you just used.
Yeah.
Is that our final answer? Since you
So that would be the fit, right? So that's our prediction. Yeah.
that would be the probability, right?
That's the probability.
Okay.
Yeah, I think it's incorrect on this one.
Answer number
15.
50. So I guess it was wrong on practice. Right?
Yeah.
Okay.
Did anyone actually get right there? I don't know what the correct answer is supposed to be.
Point. Well, the correct one was one that you got. Right?
Yeah, that's the actual correct. I don't know what it's saying on the practice test. So.
0.56.
0.56.
I think it's 0.59.
Oh.
That was good.
Is that updated?
Yeah.
Okay.
So for number 14, you would just do the same thing and plug in 3.2 for the GPA and 2.2 for the GPA. And,
Okay, I'm gonna cover this one in a little bit because there's like a bit over logistic I want to do like this cohesive.
Okay.
Yeah, it really covers like the fact that it's like 3.2 to 2.2, how you can do that.
Okay.
That can. So I'll cover that in a little bit. Remind me if I don't. Anything else before I start going through a spiel? Yeah.
Can you go over 17?
17? All right, so this is also in the big logistic thing. And the correct answer actually I think is 73. And it wasn't correct for a while. Yeah. I'll cover that one a little bit here too. I'll be one cohesive thing. Yeah. Anything else besides logistic regression? I'm just gonna do logistic regression. Okay. So logistic regression. Like I said, I think the main differentiator between the good scores on the exam and the not so good scores on the exam is going to be doing the math back and forth from like log odds, logit, and probabilities. and interpreting like that the positive values is still going up. Okay, so first off, why do we do a logistic regression? Why don't we just do a linear regression? Does anyone know? Why are we making so much trouble out of this?
I mean, like probabilities with binomials.
Sorry?
Probabilities with binomial variables, where it's like only 0 to 1, you can't really like it's not continuous, so.
Okay, yeah, it's not continuous, but why is that trouble? So let's say like I'm doing, like one application I've seen of this is a company's trying to make bids for something, right? And like they're bidding for a project, maybe to do the AC for McCombs, right? And so they would like to bid a high price, they'd like to be paid quite a bit to be contracted to do that, and at the same time they want to win the bid. Okay, so maybe they've done several projects that are similar to this, and so they won a few of these when they bid that much, and they lost these when they bid this much, right? And so you can see how it'd be a big problem for them that they want to like bid enough that they're making a pretty good amount of money, but they also want to be able to like have good chances of winning. I have this the other way around. So this is going to be losing the bid. This is going to be winning the bid. And you see like the lower price projects, the lower price bids, they tend to win. The higher price projects tend to lose. So why can't I just do a linear regression? I mean, that would work, right? I could do this. And then that would demonstrate that the higher I bid over here, the more likely I am to win, right?
Are you trying to find like how many bids are going to win?
So I'm trying to figure out like what would be a good bid for this project. Let's say I want to like, I mean I still want like at least 40% chance I win, but I need to also price it over some value to even cut even, right?
Want to find the odds maybe of winning given a certain value.
Okay, yeah. So we could look at the odds instead. So what? First off, why don't I just do this? Is it inaccurate? How do we know that? Why are we doing logistic regression at all? This is pretty easy, right? Yeah. So yeah, it's categorical, but if I want to know the probability, that's between 0 and 1, right? All right, head scratcher, right? So I mean, the main reason why is actually over here is pretty good. Over here in the middle, it's pretty good. But the trouble is when you get to the low probabilities, because let's say over here, you know, at this point it says I'm going to be getting like negative 0.2. But we know that's not true, right? Like we know that it's completely inaccurate because the you can't have less than 0 on your probability. Makes sense, right? Okay, so that's why we came up with odds, which actually odds probably came along before probability, because if you know, like horse racing or something like that, everyone uses odds there. It's actually pretty, it's just, you probably, I don't know how many people gamble, but it's pretty intuitive. It's basically just how many times you'd win for every time someone would lose. So a horse has 3 to 1 odds, like it has a really high chance of winning.
Like 75%.
Yeah, so how do we convert that to probability? So this means that the probability of winning is P. This is 1 minus P. So if this is 3, what's the probability of winning? So what's P in this case? 0.25?
Minus 3 over 2. I'm sorry, for the total.
Minus 3 over 2? So yeah, 0.25 is right. And you can just, it's hard to do it in your head unless you're used to it. So I recommend doing the full math on it every time, but you can't see it's 0.25 because it's 0.25 over 0.75. This is 3 times as much. Oops, the other way around. 0.75. This is 3 times as much as that one. Right? So odds is a good way to go, because now odds no longer go from, probability just goes from 0 to 1, but odds can go to infinite, right? What would be infinite odds?
Almost 100%.
Yeah. If you had 100%, because the bond would be 0. So you'd be infinite odds. That would be, you know, the chances of my name being Will. Yeah.
For converting the odds to probability in that example, couldn't one just use 3/1 and let's just work from there to find the probability?
I'm sorry, can you repeat the question? I didn't quite understand.
From converting from odds to probability
Yeah.
in that example, wouldn't one just use 3/1 and just work from there?
Yeah, so 3/1. So we know that P has to be less than 1 as well. So yeah, to do this by math, I would multiply both sides by this. This would be P equals 3 times 1 minus P. And then you'd have to bring all the P's over to the same side. So this would be P, 4P is equal to 3. I'll move this one over here. P is equal to 3/4, which is the same thing as we got from just doing it here. And if you're not sure, then you can do it by hand. Or else, actually, R has a nice friendly functions for doing everything, so we don't have to think. 3. Oops. What was the library? Hold up. Car. So if you download the car library, it has a nice feature called Logit. I need inverse Logit. Sorry, one more time. Boop. So I download the library boot. I now do inverse Logit of 3, and that's still not right. Oh, I'm not doing Logit yet. We're not log odds. Sorry, not a quick one to it. Sorry to confuse you guys. Yeah, so that's odds. Yeah.
One under the P, like the 1 minus P, does that one correspond to like the 3/1 odds?
Right, so that's the probability of not winning.
Yeah.
Yeah, P is probability of winning. This would be the probability of not winning. Yeah.
What was the kind of ending on that question you posed about why we even bother with logistic regression?
Yeah, so the main problem is that I'm going to get probabilities that are less than 0 and greater than 1, which is completely inaccurate. So it's actually pretty accurate here in the middle, but it's not accurate on these edges. And so when we do the logistic regression, we make an S-curve, and it makes it like this. And you'll actually notice that in the middle, it's spot on almost with linear. But on the edges here, it's not good. Because it curves. Okay, we're just basically working with the bounds, the fact that things have to be between 0 and 1. That's the whole reason why we do these logistic regression. So we're just doing a bunch of transformations to make it so we can do a linear regression and only be working with values between 0 and 1. And you can see that when we're working with the really small probabilities and the really big probabilities, it's going to be important. If you're actually working with probabilities that are between like 0.3 and 0.7, I don't want to confuse you guys too much, but you actually can do a lot of stuff with just linear regression and just forget about it. Okay, so that's why we're doing logistic regression, and that's what odds are. So odds are still not perfect, because where do odds go from? Where do they range from?
0 to infinity.
0 to infinity. And we need to make them range for linear regression from where to where?
0 to 1.
Negative infinity to infinity. Yeah, close. So how do we do that transformation? Where do we go from there with odds?
Log odds?
Yeah. So that's why we use log odds. So that's why we get log odds. That's why we work with log odds. That's why we make it so complicated. Okay. So just review quick. Hopefully this is review for everyone. The log function. So only a couple of features I'll remind you all of here. Basically, if I have a log of, let's say, x times y, that's the same thing as the log of x plus the log of y. Right? That's one quick thing to remember. And that's log of e to the x is equal to x. Right. That one I think comes in handy a lot. Okay, so any questions on that? Does it make more sense about why we're doing logistic regression now? Oh.
Yeah. Is it log dx or like ln? Like natural log?
Whenever I write log, I mean the natural log, which you might have learned in high school as
So this isn't
ln.
This isn't base 10 then?
Yeah, we never use base 10 in stats. Everything's base E. Yeah, I haven't used base 10 since, yeah, a while. Okay. Why do I do this? Log odds regression. Okay, so so how do we interpret this regression now? So what do these numbers mean? So what's the y variable on this regression? It's a linear regression at this point. It's just a little more complicated with the generalized linear regression. What's the regression equation here?
It's -6.29 plus GPA times 0.39 plus SAT score times 0.005.
What was the SAT story?
SAT, or 0.0054.
Okay. So that equals what?
The odds.
Yeah, that equals the log odds of emission. So how do I write that? The log odds of emission.
It's a mouthful, but log is a probability of getting in over 1 minus the probability.
Yeah. Yeah. So it's definitely a lot more algebra than the other parts of the class. Okay. So you could actually do everything with this equation. You could calculate your probability of emission at any point with just that. So if you're good with algebra, you have this, you're set. You can answer all the questions. Yeah.
What letters did you use for next to P, next to P over 1 minus P? Is that Y or?
Yeah, I just said, instead of writing all this out, I just said beta times the X matrix, which is all of this. Same thing as above. Yeah, so it's a linear regression. So now we start doing a little bit of algebra. So obviously I don't want to work with this nasty log, so I'm going to exponentiate both sides, right? Because the exponent of a log is just what you have on the inside. So the odds are equal to the, that's all this stuff, right?
What's the bottom part say?
That's the log
Equals what?
p over 1 minus p is equal to beta times x. That's just my shorthand for all this stuff.
Oh, okay.
Yeah, I don't write that out every time. Okay. So this has a bunch of components that are being added together. Anyone know the features of an exponent I can use to kind of work with that? That's one way of looking at it. So like e to the 2 plus 4, right? That's equal to e to the 2 times e to the 4. Right? Do you remember that? That's kind of a nice feature to use here. Because now this turns into the odds is equal to exponent of negative 6.2 plus the exponent of 0.39 times GPA plus the exponent of 0.005 times SAT.
I thought it was multiplied.
Oh, yeah. Thanks. Okay. Yeah, just what I said. I forgot. Okay, so why do I want to write it out this way? What's this question up above? Where's the one with the someone has slightly higher than someone else? Yeah. So Albert and Beth have the same SAT score, but Beth's GPA is 3.2 while Albert's is only 2.2. Okay, so that means I don't know is it SAT? They have the same SAT score, so I don't know what the difference is there. And the intercept's the same, right? So I'll just call this times this. I'm running out of letters. This times this, I'll just call that A, right? We're changing SAT scores, or we're changing GPA? I got really messy there. Did I lose everyone? I don't want to just keep moving on. I did. Yeah.
Just a quick question. So when you put it into RStudio,
Yeah.
if you do exponent and in parentheses, do you leave it in addition there, and it's only when you break it apart that you start multiplying it?
Yeah, so where it is in R is being added still.
Okay.
You need to exponentiate everything that's in it.
Right. So you exponentiate the added equation.
Yes.
It's just when you break it apart individually that it becomes multiplied.
Right, so once I exponentiate the insides, I'm basically multiplying each of them by their exponential.
Okay.
Yeah.
So what is the A represent again?
So I'm summarizing everything that's not GPA related into just A, because I'm being told that that is the same between both Albert and Beth. The only thing different between Albert and Beth apparently is their GPA. So essentially all these other things are constant. I'm just looking for the change. If I move up 1 GPA, 1 point GPA, what does that do to my chances of admission? That's another way of wording this question. Yeah. Okay. So
So when they say chances, do they mean odds or do they mean probability?
let's say they're let's do their odds in this case. It's easier with odds. Yeah.
Is that what they mean though?
I don't know what you meant on the question exactly. I didn't rewrite the. Sorry.
So it seems kind of ambiguous.
Yeah, I agree. I tried to. I looked over the exam a couple times to make sure it's less ambiguous. I thought that. Yeah. I'll try. For the pedagogical reasons, let's try and go with odds in this case. So how would that change the odds? So which way would it go first off? If I increase GPA, well, this one's everyone knows kind of from how admissions work. But which way does it go? And how can you tell from stats? And how would you know that?
Because it's a positive number.
Right, exactly, because it's a positive number. Trouble with using these models that everyone kind of knows what's going on is that you can kind of intuitively tell that if someone's GPA goes up, their admissions go up. So by how much so? Right, so this is going from what? 2.2 to 3.2. So I can just plug those two in basically. So I want to see the percentage change. I just do exponent of 0.39 times 3.2 minus the exponent, or divided by, sorry, 0.39. What's the other number? 2.2? Sorry, can you all read anything I'm writing? No? Okay. Is this math clarifying or am I complicating things for y'all? Yeah.
Did you just plug in 1 to the GPA, so the change is just 1 point, from 3.2 to 2.2?
Yeah, that would work.
The answer is 1.48, and why is it? Is it just 0.48% because it has to be between 0 and 1?
Yeah, so that's not necessarily between 0 and 1, because it's like the percentage increase. Like I could triple my odds, I guess. But so I do exponentiation of 0.39. You see that it's 1.47. So if I want, that's like my odds of being admitted were maybe 3 to 1 before, and basically I just multiply that by 1.476. So it's like it's a 47% increase. What we're looking at. Yeah.
I'm following all your math, but I'm confused on the last step. Like, what exactly is that?
Yeah, this was a messy.
So is that like, well, just the answer of that. So whatever you put there, is that the log odds or is that your actual probability?
That's gonna be the change in the odds.
So, but not probability.
Right. Yeah. So that was the confusing thing about the way that it's worded in question, because you can't really tell how it changes the probability, because you have to know what the probability was before. Because the log transfer, the odds transformation to probability is not linear, right? So it changes wherever you're at.
So this changes the log odds by 47%.
This would change the odds by 47%. Yeah, there's three. There's right. So I already took when I did the exponentiation, I got rid of the log part. Yeah, it's really confusing because there's like 3 things we're predicting, right? There's the log odds, which is what we get from the regression. There's the odds, which is like the middle part, and then there's the probability, which is what everyone's been doing in this class up to now. So there's 3 things.
I don't want to confuse you or anybody, but like if this doesn't make any sense, you can shut me down. But so given that like 1.47, that would be the increase in the log odds. No, that would be increase in the odds.
Increase in the odds.
So could you say like, well, the odds go up by like 1.48 to 1? Could you say that the probability would then be like 1.48 over 1 plus 1.48?
I have to work on the math of that, but I don't think it's quite so clean, because it'd be like I guess what you do is you do P1, the original P is equal to 1, right? And so P2 is 1.47 times that. Yeah. And solve for P2 over P1. Yeah, I guess you could do that.
So on the equation P over 1 minus P equals exponential, all that right there, your second line down. If we had the predictors, yeah, now. If we had the predictors for GPA and SAT, would that give you what the probability equals to? So that gives you the odds.
That'll give you the odds, and from odds you can get
solve for probability. Okay.
Right. But there's a one-to-one relationship. There's only one probability that comes from an odds. Like if you tell me the odds, I can get the probability somehow.
Okay.
Yeah.
So we can change this to the change in probability.
Yeah, you could get the change of probability by doing this part, but that's few too many steps in my opinion.
We would just plug in whatever number we got when we exponentiated 0.39 into either P.
Yeah, I'm into new territory. I haven't done this in a while, but yeah, I think you should be able to solve for P2 over P1 with that. Yeah, I'm sorry, I haven't looked at this enough to talk about it much. Yeah.
How does one interpret the coefficient of the high school GPA?
Right, so the quick way you can interpret this is whenever you look at this, you right away know the direction, right? And it is like 1-to-1. Just because I made the log transformation and I made the odds transformation, as long as it's moving up, the probability is moving up, right? Like it's just convoluted, but it's still the same directions. The directions never get switched. So if it's positive, that means that the high school GPA is going, as high school GPA goes up, the probability of admissions is going up, the odds of admissions is going up, and the log odds of admission are going up. They all go the same direction. It's just like the scaling that gets messed up.
So one can interpret it as like as an increase in high school, as an increase in a high school GPA, the odds that one gets admitted 48% higher.
The odds would have to be the exponentiated 0.39. You have to exponentiate it first. The log odds get 0.4 higher. Yeah. Okay. Yeah, I would do everything very slowly when you start doing the log odds and the odds. Because remember, it's log odds first when you have the regression.
So it's, okay, like that's the log odds, so is it, odds the, like an increase in the log of like high school GPA is 0.39?
Yeah, so we're not transforming any of the x variables.
Okay.
So you could do an x transformation, but we don't do that in this class. But yeah, so the variables are as they read.
Okay.
Yeah. Okay, so there's one other thing I definitely want to go over. Where is probability 0.5? What's the odds of 0.5? 1-to-1, right? So that'd be odds of what? 1, right? Because 1 over 1 is 1. Yeah, so P of 0.5, so equal chances, odds are 1. What's the log of that?
0.
0. So what value would these numbers have to add up to be to give me equal odds, or log odds of 0? Like I just said it. Then add up to 0, because the log odds is what we're working with here. So we're trying to see where we get equal chances. These things have to add up to 0. Does that make sense?
Say that again.
The odds add up to 0. And probably.
The log odds add up to 0. Yeah. Okay, I'll do that with visually so you all can see it. Okay. So I want to know the probability is 0.5. That seems like a logical place, right? Because that would mean that it's equal chances. So any higher, I would guess that it would happen. Any lower, I would guess it would not happen. That's why I chose 0.5. Okay. So what's the odds for that? Well, odds is equal to P over 1 minus P. So that's 0.5. 1 minus 0.5. That's equal to 1 over 1. So 1, right? Odds of 1 equals equal chances. Okay, so what will be the log of this? What's the log of 1? Yeah, so the log odds is equal to 0. Now, what is this regression finding? Regression is finding which one? Log odds, odds, or probability? Log odds. So if we want equal probability, what do these coefficients add up to? 0. Yeah.
So the coefficients have to add up to 0?
Well, the coefficients times what the x's are.
Oh.
So if I want, the reason why I'm saying this is because let's say you have a high school GPA of 2.5. What would your SAT scores be to give you a 50% probability of being admitted into some college? Well, all you have to do is you say, okay, negative 6.29. I'm going to add 3 times 0.391. 0.2934. Add 3 times, what did I say, 2.5 times 0.391. So I still have negative 5.31 to go here. So I have to have an SAT score of that divided by 0.054552. That doesn't make too much sense, does it? Yeah, negative. So I have an SAT score of 974. So I got a pretty good chance of doing. Does that make sense? So that's like one of the examples of the back of the note card calculations. I'm kind of saying is pretty important for an exam.
It makes sense though, because like you did the log roll, you proved that rule, e to the 0 power, right? E to the 0 equals whatever it is inside the parentheses. So
Yep.
parentheses is like the odds, right? So your odds would be that.
Yeah, I'm not familiar with that term, but that does make sense math.
Okay.
Yeah. Is it the log
Like log roll.
log roll?
Yeah.
Okay. Cool. Yeah, so does this make sense? Hope it does. Are there any questions about this? I would say if you have any trouble with this, then you want to work on that part. Yeah.
So, on the interpretation, so instead of increasing odds, will be increasing log odds?
So we're doing both. Because anytime you increase the log odds, you're increasing the odds. It doesn't change the sign. There's no transformation we do that changes directions. All the transformations are changing scale.
So you would just take the increase in the log odds and you would exponentiate that, and that would give you the increase in the odds?
Exactly. Yeah. Yeah. So that's why we exponentiate things, is we want to get rid of the log part. Okay. Yeah. So what was the other? So we can go back to these. What was the other one? 17. Okay. So hopefully this one makes more sense now. You see why we're using odds here. So how would I do this? Yeah.
You just exponentiate the SAT score, increase them 100 times, so everything
Yeah. So exponentiate 100 times SAT score coefficient, you said? So exponentiate 0.0054552 times 100. And so I'm multiplying my odds by this. So what's my increase in odds percentage?
73%.
Yeah. Just 1 minus that. Okay. So should I work through what happened there, or are y'all getting that?
No, that makes sense.
Awesome. If it's making sense, you're doing well for the exam. If it's not, I can go over again. So that's something I'd really like to make sure y'all get.
For number 19, we just do the what we were talking about earlier, where we take the standard error and we add it to the mean value. Or
Yes.
would we multiply the mean value by 3 and then add the standard error and subtract the standard error, and that gives us the range?
Sorry. Okay, so plausible range for the GPA if they do 3 extracurriculars. So the transformation is actually on the x variable, right? Right, or is it on the y?
It's on the y. So it's a log.
Predicting high school GPA from the log of extracurriculars. Right? So this would be transform on the x variables, the predictors. So if I have a transform on the predictors, and I get a, if I want a range of possible y values, do I have to do anything special there?
You have to exponentiate them.
Possible range for the predicted GPA if they do 3 extracurriculars. So I don't think you need to do any different things on your prediction there. And the reason why is because, so the model, do I have this right there? So, yeah.
So you would just do predict.lm.
Yeah. So I'll do this real quick. So first I'm just doing the log of extracurriculars and calling it log extras. And then I'm making a linear model of my high school GPA as a function of what I just made. Right? And so the one trouble here is that what do I put in for my x variable here? So log extras is the x variable. It won't even work if I put in just extracurriculars. And I don't put in 3. That's be the common mistake. You put in the log of 3, like you just said. For the prediction. Yeah. And be sure when you're doing this that your lower and upper bounds is not this number and this number. It's this number and this number. I've had that happen a few times. Multiple students have done that, so if you did it, don't feel bad.
Can you say that again?
When they ask for the lower and upper bounds of a prediction interval, it's this number and this number, not this number and this number. This is the fit. This is like the most likely value. It's a very confusing way of ordering it, I agree, because you would think they'd be like the lower range, the upper range, and then like your best fit here. But yeah, and I've had multiple submissions, including on the midterm, where people use that fit value as the lower bound. So that's unfortunate. Yeah.
I'm just trying to understand between what you did and what the answer shows, because on the answer it shows like the less extracurriculars, but it doesn't have a log extracurriculars. So will it still give the same answer?
Yeah, I just did it too. Because I mean, if you build the model, you build it with log built in. So I thought.
Oh yeah, you can do if you do it with log built in. I think you might be able to do it that way.
Yeah.
But yeah, I did it by transforming log that extracurriculars first. If you get the same values by doing a different method, you're fine. Like there's a lot of different ways to do the same thing in R. So I'm not gonna tell you to do it.
Yeah.
You can only do it this way. I'm just gonna teach one way. I think this is like the clearest way, so that's why I do it. Okay. All right. So do y'all have anything else you want me to cover on the
Oh,
practice?
yeah, not on the practice exam. I'm just wondering, well, I guess it is on there, but can we go over AIC and BIC?
Sure. So I'll go over a little bit of that. First off, I do want to prefix that I don't think model building is as big on the midterm, and I feel free to say that. it's definitely covered much more on like the project. And the reason why is because model building is a much more it's a much more subjective sort of thing based on what you're trying to do. With that being said, I do want to start off first by saying I think one of the biggest things, concepts that a lot of people forget, is that when you can use R squared for deciding between models and when you cannot. So if I transform the x variables and I have the same number of x variables, can I use R squared?
Yes.
Yes. Can I use adjusted R squared?
Yes.
Can I use AIC?
Yes.
Yes. Okay. Let's say I have one model with 3 predictors and one model with 1 predictor. Can I use R squared? No. Because it doesn't take off for the fact that I have more predictors. Can I use adjusted R squared? Yes. Can I use AIC? Yeah. Great. So let's say I transform the y variable. Can I use R squared? No. And the reason why is because, like, let's say I'm predicting the log price of diamonds. And I have one model that predicts the log price of diamonds. I have one model that predicts the price of diamonds. So where are my units of being off with the log price of diamonds? I'm on like a log dollar scale, right? And the other one's on what? Dollars. I can't really compare log dollars and dollars. It's like comparing apples and oranges. So you can't use R squared in that example.
So what would you use in that?
Yeah, if you start predicting your y variables, it's not as easy to go into. But basically, I would mostly go into, I'd probably look at which one has a better fit. Because if I'm doing transforms, I'm looking for more graphical, like if it fits the linearity issues and stuff like that. Yeah.
Okay, so
Yeah.
I know it's not really on there, but it was on the practice exam. Like, how do you know when AIC is like good or bad? Does it like go up or?
Yeah, so AIC is like the R squared and stuff like that, but lower AIC is better. That's the main thing to remember, that you want AIC to be low. And it's not like it's so intuitive that I can just look at it and just say something. If you just told me you have a model and you have an AIC of 436, I would say great. I don't know anything, I don't have anything to tell you. It's mostly for comparing models. So it's really kind of meaningless when someone just tells you their AIC. That being said, the main thing that's different between AIC and like R squared is that adjusted R squared takes off a little bit if you add parameters. AIC takes off more than adjusted R squared. And if you want to learn the other criterions, like BIC takes off even more than that. But AIC is kind of like the one that most people like nowadays. I would say it's probably the most common for model building because you can go between different types of models with it. Yeah?
So the AIC gives a harsher penalty than the just R squared?
That's right. Yeah. Yeah, AIC is pretty flexible. Like if you start working with much more, I'll do like ordinal models and more complicated models, and I can compare those models with linear regression with AIC. So that's why everyone uses it at the higher levels too. So, yeah. Okay, so and then with model building, what that step function does, and so if I have some big model, let's say M3. Is a function of all equals that. All right, so M3 is huge. And I want to cut it down. Well, I can just use the step function. And what step is doing is basically is adding and taking away variables from the model until it minimizes the AIC. That's what it's doing. And you have to know the details of it. But essentially, it's going to find a better model than most people can do by their hands. So in this case, I think it kept all of it, probably. I would guess. Yeah, it kept all of it. And so that's to be your minimum AIC model. And it's true that by using the step functionality, like it seems a little silly with just having 3 variables here, but like let's say we're working with the add health data set, which has like 1 million. Like you would not want to do this by hand, so you'd have the computer run, and it would take quite a while. This is the sort of stuff that you like run your computer and then leave it overnight, sort of thing for the big models. That's kind of what it is. I don't think it's used probably as much in business, but that's what it does. And yeah, it won't find the optimal model necessarily, but it does a pretty good job. Like, people use it everywhere for that reason. Yep. Sorry? Okay. Yeah.
On number 4, it's talking about adjusted R squared, and so you can use it like when you transform things. Just R squared you can't use when you're doing transformations, like compare between models.
Okay, so with transformations of predictor variables, models without transformations of predictors, yeah, this should be just fine, because R squared is really, it's just not good whenever you change the y variable, right? Because like you can think that my units of error, if I'm predicting price and I just change from caret size to the log of caret size, my errors are still going to be in terms of dollars. And it's going to be dollars to dollars so I can compare them. So it'll be fine. Yeah. Just look out that you can't use the R squared if you change the y variables. That's just the main thing. Everything else is usually fine. Yeah.
In the exam tomorrow, if there's a question that wants us to create a model, will it specify whether it's a logistic regression model or a normal model?
Okay, so I don't remember if it specifies exactly, but you should be able to tell right away based on what are you trying to predict. So if the thing you're trying to predict is a 0, 1, like a yes or a no, there's no middle grounds, it's a discrete variable, then you should use logistic. And for the reasons I showed before, because now you can't, if you do linear regression, you can have a probability of negative 0.2, which don't ever write a negative probability because I'll take off because it's a negative probability. Yeah. Okay. I think there's a lot less material covered from the first exam to the second exam than there was before the first exam, so I'm not surprised that we're running out of topics here. There's less to it than I think everyone's thinking. Yeah.
On number 7, it asks which one's the most practically significant.
Oh, yeah.
If you get the z value, you could get the.
So for practical significance, again, it's not based on your p-values or your z-values. First, you always just check if things are statistically significant, because things cannot be practically significant if they're not statistically, right? Because the whole direction of the sign can be switched. So these are all statistically significant, and if I'm trying to imagine what's the most practical, I kind of just work out in my head what's going on here. So this first variable is weight, I think, right? LWT. Yeah, pounds before pregnancy. I don't know why L, why LW. And so the lighter someone is, the more likely they are to have a low birth weight. And then if the mother was a smoker, the increases the chances of a low birth weight as well, right? Increases the log odds by 0.68, so it increases the odds up and it increases the probability. Additionally, if they have hypertension, which is like a 0, 1, the log odds go up 1.822. Okay, so then I play it out in my head like, okay, what's a reasonable, the trouble is that we don't say like what the standard deviation is with mothers, so I don't know like how low weight someone who has low weight is. I mean, know how many pounds, but let's say like 20 pounds. Let's say a mother who's like 20 pounds under the average weight of a mother. So how much would that affect the log odds? Like 0.4, right? The log odds would go down by 0.4, or go up by 0.4. See how I did that? It said 20 times this. So that's not the same amount as smoking. Smoking is still a lot more. So in my mind, I kind of say, all right, well, smoking is more significant than low weight. What about hypertension? Well, hypertension is just 0, 1. And you can see it's almost 3 times as much as smoking. So I think hypertension is by far the most practically significant for figuring out whether it's going to be a low birth weight, maybe or not. That's how I worked through it. Yeah.
So practical is just based off which variable affects
Yeah, so practical is like the most hand-wavy term in statistics because it's kind of like just what's the most important for what you're trying to do. So the trouble is that we don't give you enough context because like in the real world, you're trying to do something, right? So in this one, like I'm assuming that they're trying to figure out which variable is the most significant in predicting if it's going to be a low birth weight. And so basically, if I'm evaluating some mother and I'm trying to say the chances of them having a low birth weight, it's like, yeah, she smokes, that's not going to be good. She's really tiny, that's not going to be good too. But also she has hypertension. The hypertension, that's the big one.
If there's comparing two models, would you also look at the AIC if it's like lower, the lower AIC would be more practically significant?
Yeah, so saying that which model is more practically significant than the other is kind of a little bit different. But your prediction will be better with the lower AIC model than it will be with the higher AIC model. Yeah.
When do you use pseudo R squared?
Oh yeah, I wanted to cover that too. So pseudo R squared is like, people really liked R squared, and people wanted something similar to it with logistic regression. But it's really not quite the same. So I'm not a big fan of pseudo R squared, but to teach what it is we're following kind of the same formula as R squared, which is 1 minus the variance divided by the null variance. So instead of using variance, we use something called deviance, which is like logistic regression's version of variance. So just like what we're saying, it's just 1 minus the deviance divided by the null deviance. Okay, and it's a measure of fit in some ways, because if we had 0 deviance with the new model, like we perfectly predict everything, which is impossible, but if we did, then we would have 1 minus 0, so we have an R squared of 1, which, you know, an R squared of 1 with a linear regression means that you're perfectly predicting everything. If we're not doing any better than like the model before, then it would be 1 minus 1 minus like 100 over 100, which would be 1. So 1 minus 1, R squared of 0, which means that the model has no prediction power, right? So it's kind of analogous to linear regression's R squared. That's the reason why it's invented. Now, McFadden's pseudo R squared, the trouble with it is that the values aren't quite the same. So like, if you got a 0.05 of logistic regression as your R squared, that might be an okay logistic regression, actually. If you have 0.05 of your R squared on a linear regression, that would not be so hot, right? So that's what it is. And to calculate it, then all you have to have is logistic regression. So let's say it's M1. And it's just 1 minus M1 deviance divided by M1 null deviance. And so I have a pseudo R squared of 0.1586. Now, if that's good or bad, I'm not entirely sure, but you can compare models with that, because if they have the same null deviance, I'm just basically comparing which one has the higher deviance, which I want the one with the least amount of deviance. Okay. Yep.
So, yesterday I think we were told that like any pseudo R squared value between 0.2 and 0.4 is good. So this one being less than 0.2, like you can say it's not good, right?
Okay. Yeah. I don't. Okay. Yeah, I think that's what it says in the lectures. Yeah.
Yeah.
Yeah, that's fine. See, really, the best thing is the prediction. Like, if you're predicting 80% of them, when before you were guessing only 40% of them, to me that's the good. That's when you have a good model. Yeah.
Can you give an example of which does a mathematical equation e to the power of x times y, and then just basically trying to separate it?
So you're saying if I have exponential x times y, so that's e to the power of x times y. right? That's going to be, so let's say x is 1 and y is 2. So that would be e to the power of 2, right? So that would be e times e. What's the way of doing this?
So how did you show it as a logistic regression formula? They say like e to the power of beta 9 times beta 1, beta 1.
So when you add these, so x plus y, that's equal to e to the x times e to the y. So that's the main one. That's what the transformation you're looking for is. This one's not as easy, I think. Yeah. Sorry, is that what you're looking for? Because that's really more about it. Like, 'cause when you're doing the logistic regression, that's why you have that 100 times the coefficient when you're seeing how much it goes up.
Well, I was just trying to figure out how would a logistic regression formula would look like with e to the power of x times y. So wouldn't it basically be like e to the power of beta 1 times or beta 1 times beta 2? Or different.
Yeah, so it'd be beta 1 plus beta 2 because you have that linear regression when you do the log odds. So that's why we use this form a lot when you're doing that. That's why you multiply the odds by coefficients.
What about the one above?
The one above? So if this happens, I don't think there's a quick way of splitting it out. Yeah. Yeah, that one doesn't transform as quickly, I think.
So the most important thing is just focus more on the one above.
Yeah, the one on the bottom, which is e to the x plus y. That splits out to e to the x times e to the y.
The e to the power x times y is that another level?
I can't think of any quick transformations off the top of my head. There might be one I don't use very often. No problem. Yeah.
Can you explain the likelihood ratio?
Likelihood ratio. Yeah. So an LR test is a good way of checking if this model is superior to the previous one, or if the, because you know that if you add terms, it has to improve the model, right? And the reason why is because, like, let's say that I add the number of chickens at my neighbor's house to this model, like, it can just set the variable equal to 0 if it doesn't have any effect, right? It can't get worse, the prediction power. So how you check if this added power is worth it is essentially that the likelihood increased by enough. So that's all it does. Yeah. Do you want to go through the math of it, or do you want to do like much?
Well, isn't like gonna be only estimate?
I think just the fact that what an LR test is. Yeah. Yeah.
Can you explain?
Yeah. Actually, I haven't used that one too much. An LR test compares one model to the other. That the improvement is only due to just chance, essentially. And so it's very analogous to an F test between one linear model to another linear model, but it's just a logistic version of that, I would say. There's a lot of things that are almost exactly the same from linear regression that they try and do the same thing in logistic, because people learn linear, they want to move it over. Yeah.
In the model, you can have either AIC or just R-squared. You cannot have both.
No, both of those measures can be applied to that, and you can compare. And usually R squared, the model you pick with adjusted R squared usually matches up with the model you pick with AIC. So they're just different ways of doing it. And that's kind of the thing that like goes through trends. And I'm gonna say that the more popular one, the one that seems to have the better prediction power, is AIC. AIC seems to win. So, yeah.
Can you go through 18?
18.
I'm just not sure on the 0.24 and then the one about the intercept. Sorry, the no X.
Which one? The
The first one and the last one.
first one, the last one.
Confused about those.
Okay. So, so this is from the interesting, from the log of extracurriculars. So what's the log of 0?
The error.
Yeah. So e to the power of what is equal to 0, is what we just said. So this model won't actually work when you plug in 0 extracurriculars. So you can't really predict a GPA of 2.0. Yeah. That one's kind of a tricky one. But essentially, if you just like try doing it, just try plugging in like log of 0. You know, it's not gonna work. Okay. So you probably got this one, right? And then you increase of 1 units in log extracurriculars is associated with a predicted GPA that is 0.34 higher. I'm not sure if I didn't make the model. I don't have it off the top of my head, but there we go. Summary 2. Yeah, that looks right. Because if I increase my log extracurriculars by 0.39, yeah. Okay. And an increase of doubling the number of extracurricular activities is associated with an increase of 0.24 points in GPA. Okay, what do you think about that one?
I was just like not sure where to put the 2, like when doubling it, like within the log coefficient or like, yeah.
So we're doing beta 1, I forget what the term is, times the log of 2 times number of extracurriculars, right? So remember that the log of something times something is equal to the log of 2 times the log of, remember that split? So that's why I show that one. This is equal to beta 1 times the log of 2 plus beta 1 times the log of number of extracurriculars. Does that make sense?
Yeah.
Yeah. So this is what we had before, right? So I increase by this. Yeah.
And you don't have to exponentiate anything. I mean, the question is really
Yeah, so doubling the number, so it's this one. Increase of 0.24 points. So it's going to be a linear increase in GPA, because this is just equal to GPA. There's no transformation, so I'm just linearly adding that much when you double it.
Wait, so that's true.
If beta 1 times log of 2 is equal to 0.24, that is correct. Yeah.
I was just gonna say you could also like I think guess and check on this one. So
Yeah.
you can just, like,
If you're in doubt and you have time, like yeah, definitely you can plug in stuff. I recommend double checking your answers whenever you do. Like that's just good test taking practice. You know, like if you can do it 2 different ways, I feel like you really check that you did it right. Yeah. Because I catch a lot of mistakes when I do tests like that. Okay. Y'all feeling better for the exam? No? Yeah. Like I said, I think working with the log parts is definitely like the hardest, and if that's hopefully what y'all picking up too. I think this is probably like, if you're strong with algebra, that's good. If you're not, I would recommend just it's a little bit not fun, but take the time to like try doing a few of these by hand, and I swear you'll get way better just spending like 15 minutes or 30 minutes sitting down doing it. Not fun, but it'll pay off. Yeah.
So earlier you made a model 3 and model 4 on the summaries below. So could you tell me exactly what you're looking for in those summary models?
I forgot what I did here. Oh yeah, so summary 3, I was just demonstrating the step function. And so model 3 here, I just did the linear model of high school GPA as a function of, I just said everything, that's what the dot does. You don't have to know that, it's just a shortcut. And then, so then I have the summary of model 3 there, and I use step function, the stepwise regression, to basically let the computer fits my model in a way that improves the AIC, which it actually, because there's only 3 variables here, it ended up saying that, yeah, it's actually the best model keeping all 3 of them. So that's what happened there. I was just demonstrating the step functionality. That was it. You don't need to know too much details about the step functionality. It just picks the best. It tries to pick the best AIC model out of what you have.
Model 4 would technically be like the best model then after doing the step function.
Yeah. Okay. Yeah. I hope you all are feeling better. Anything else you want me to go over?
I have a quick question on the homework.
Yeah.
6. So like, I know on homework 6 the data income is increasing by 1,000 rather than like increments of 1 we're used to basically, right? So like they would round up to thousands. So like you had 49,000, the next you could get up to is 50,000, right? So when you have like log odds of that, if you have the coefficient, is it increasing by like 1,000 income, or is it still just $1?
So it depends on what you use as your x variable. But if your x variable is based on units of dollars and you're increasing by 10,000, then you need to actually increase it by 10,000. And log odds is changing linearly. So that one's going to change just that times 10,000. The log odds are. And so when you exponentiate it, it's not quite the same thing because now you have to do exponent of 10,000 times that, which isn't quite as clean. But yeah.
So you do stick with like the how it's incremented, you know?
Yeah, I think so. I don't know homework 6 as well as homework I do. Yeah.
What's the difference between linear model and general model?
Yeah, so linear model was definitely the first one. And then essentially the easiest way to fit these logistic regressions is to use a link function, what they call it, and then to do a linear model based off of that. Because the reason why you can't just do a linear model after you do these log transformations to do the log odds is because your errors are no longer the same between everywhere. It's basically it fits that. It fixes that. We don't want to go too much into the details of that, but that GLM function, you can fit a lot of different models with it besides logistic ones. You can do Poisson models, you can do these different count models, you can do a bunch of different things with it. So it's a generalized linear model, we call it. Yeah. So, yeah. Okay. Well, unless y'all have any more questions, I'm going to turn off the video. Thanks for listening.